Archaeological records indicate that Galena, a lead sulfide mineral and primary lead ore, was utilized by pre-Columbian Native American populations in eastern North America for thousands of years. While some evidence has indicated that pre-Columbian societies generated limited lead pollution as a byproduct of copper mining and biomass burning, there has been no conclusive evidence that the extraction, trade, and use of galena specifically resulted in environmental impacts. This contrasts with other regions with long histories of lead ore utilization, like Europe and South America, where early lead pollution signals are widely distributed and well preserved in natural archives. One explanation for this difference is that smelting was not needed to extract lead from North American lead ores given extensive surface exposure of high purity galena deposits throughout the Missouri, Ohio, and upper Mississippi River basins. There is also little indication that pre-Columbian societies developed smelting techniques prior to European contact. Instead, lead ores like galena were utilized either in crystal form or ground into a powder. Despite this, it is unlikely that there were no environmental impacts associated with the extraction, processing, and use of galena by Native American populations prior to 1500 CE. Instead, pollution was likely expressed on a local level, which would account for the lack of widespread pre-Columbian lead pollution in eastern North America. Therefore, site-specific investigations are required to uncover environmental impacts associated with pre-Columbian galena use. Before going forward, I want to mention that in this video, I will be using the shorthand CE and BCE for Common Era and before the Common Era to describe time, instead of AD or BC, which I used in other videos. In this presentation, I go over the 2019 paper from Bird et al. In this paper, they utilized sediment cores from a floodplain lake next to Kincaid Mounds to investigate past human impacts. Specifically, Bird et al. Used geochemical and isotopic methods to quantify lead pollution and its provenance through time. Kincaid Mounds, hereafter referred to as Kincaid, is in southern Illinois on a portion of the lower Ohio River floodplain known as the Black Bottom. While smaller archaeological sites have been identified across the Black Bottom, Kincaid represents a primary locus of habitation on Avery Lake's northern shore. Archaeological evidence indicates that this site was intermittently occupied since at least 4000 BCE, with the first evidence for intensive settlement and village construction beginning during the early and middle woodland bomber phase from 300 BCE to 300 CE. Kincaid was subsequently abandoned or intermittently occupied by a sparse population from about 350 to 650 CE. After 650 CE, Kincaid was repopulated during the late Woodland Lewis phase, which transitioned into the Mississippian period sometime between 1000 and 1150 CE. The Mississippian occupation, which lasted until about 1450 CE, is the best studied at Kincaid because large earthworks, bastioned fortifications, and an extensive village were constructed during this time. Between 1400 and 1450 CE, Mississippians abandoned Kincaid along with much of the central Mississippi and Ohio river valleys, in what has been suggested to be a response to a severe 100-year-long drought between 1350 and 1450 CE. Kincaid and the surrounding Black Bottom remained largely unoccupied until the 1800s, when Euro-American settlers began utilizing the region for river commerce and agriculture. Multi-proxy results from Avery Lake, published just before this paper, complement the archaeological perspective of Kincaid's occupation and reveal additional information about pre-Columbian land use and environmental impacts. For example, the most intensive pre-Columbian occupations identified in the archaeological record were each characterized by extensive land clearance as evidenced by simultaneous lows in tree pollen and peaks in ragweed pollen, the latter being an indicator of landscape disturbance. Population increases during the bomber phase and significantly increased population densities during the Mississippian occupation were additionally reflected in bulk sediment delta 15N variations. Whereas delta 15N was relatively invariant during the bomber occupation, indicating low population densities, it abruptly increased by around 4 per mil to 6.5 per mil between 1130 and 1185 CE, suggesting that population densities reached around 60 people per kilometer squared. Delta 15N values subsequently decreased but remained elevated until after around 1460 CE, which agrees with the site being abandoned between around 1400 and 1450 CE. Three distinct lead concentration peaks are also apparent in the Avery Lake data during each of the major occupations in the Black Bottom, i.e., the Bomber, Mississippian, and Euro-American occupations. These lead anomalies remained in the sediment even after normalization with conservative elements such as zirconium and titanium, indicating that they represent excess lead in the environment. Given their temporal association with human occupations, the lead anomalies are thus attributed to anthropogenic pollution. Anthropogenic sources of lead during the past 200 years have been extensively investigated, with wood and coal combustion, ore smelting, and the use of leaded petroleum products generally implicated as the source of modern lead pollution. In the paper I'm covering in this presentation, Bird et al. Focus on the pre-Columbian lead signals, as little is known about the occurrence or sources of early lead pollution in North America. Cores were obtained from Avery Lake in 2014. Details regarding the previous geochemical and pollen proxy analysis at Avery Lake can be found in a previously published paper. In this presentation, I focus on lead stable isotopes measured from 30 subsamples taken from core A14. More information about the analysis of lead isotopes can be found in the link to the paper in the descriptions. The lead isotope results show consistent trends across all time series, with two primary features standing out. The first is a long-term baseline for the ratios of stable lead isotopes. The second is an abrupt positive lead isotope ratio excursion towards higher values during the Mississippian period between 1150 and 1400 CE that was contemporaneous with an excess lead concentration peak. Notably, no lead isotope excursions occurred during the bomber phase despite increased excess lead concentrations. These lead isotope results suggest distinct origins for the Mississippian and bomber lead peaks. Spatial variations in lead isotopes of regional ore deposits have been systematically investigated over the last several decades, providing a means with which to determine the provenance of lead in soil and sediment samples based on their lead isotope ratios. The well-defined pre-anthropogenic lead isotope background against which the Mississippian excursion occurred is consistent with an Appalachian sediment source. When plotted in lead isotope space, the radiogenic Mississippian lead isotope ratios plot along mixing lines that project towards values associated with radiogenic lead ores from Missouri in the upper Mississippi River Valley. This suggests that excess Mississippian lead concentrations resulted from an influx of radiogenic lead primarily from Missouri and to a lesser extent the upper Mississippi River Valley. This is consistent with Walt Hall's seminal work that used trace element geochemistry to show that most of the Mississippian period Galena originated from the old lead belt subdistrict in southeastern Missouri. Among the remaining, 12% was derived from upper Mississippi Valley surface deposits and 5% was from central Missouri. The Avery Lake lead isotope results demonstrate that Mississippian Galena use was a source of environmental pollution that remains as legacy pollution today. Archaeological evidence indicates that Galena was crushed and the metallic powder was ritually used as a cosmetic or to adorn sacred objects or structures. It is therefore most likely that the source of lead pollution in Avery Lake was Galena powder that was washed or blown into the lake after its use or as part of its production by grinding. To estimate the amount of Galena-derived lead contained in Avery Lake, Bird et al. Used a 2 end-member mixing model that accounted for different end-member lead concentrations and isotopic compositions. In this paper, Bird et al. Used lead 206 to 204 isotope ratios and lead concentrations of the background sediment in pure Galena for end members EA and EB respectively. The isotopic composition and abundance of lead for EA were estimated by averaging pre-Columbian background concentrations and lead 206, 204 isotope values, excluding the Mississippian lead 206, 204 isotope excursion. The lead 206, 204 isotopic values and concentrations of lead in EB was estimated using an 83 to 12 to 5% mixture of southeastern Missouri, upper Mississippi Valley, central Missouri, Galena, which have respective average 206, 204 values listed in the paper. Lead isotope values for different mixtures of EA and EB were calculated using this equation. The mixing hyperbola generated by equation 1 indicates that Galena deposition in Avery Lake contributed between 2.1 and 15.9 parts per million in lead during the Mississippian occupation between about 1150 and 1400 CE. Accounting for dry sediment bulk density and sedimentation rate changes during the Mississippian period, Bird et al. Calculated the flux of Galena-derived lead to Avery Lake. Their results indicate that a total of 1.5 metric tons of Galena-derived lead was deposited in Avery Lake as a result of Mississippian activities. Over the approximately 250-year Mississippian occupation, this equates to about 6.2 kilograms of lead per year. In contrast to the Mississippian period, no lead isotope excursion was associated with the Bomber Peak between 310 and 15 BCE. Bird et al. Suggests that biomass burning plausibly accounts for the excess lead deposition in Avery Lake during this time, given that lead is an important component of biomass combustion products and pre-Columbian societies are known to have extensively used fire to modify the landscape. Bird et al. In 2019 suggested that initial land clearance via fire was followed by frequent fire use to maintain the landscape and for domestic activities. Because the combusted biomass had originally grown in sediments from the Black Bottom floodplain, which share the same Appalachian source as those deposited in Avery Lake, it would have the same local isotopic signature thereby not altering lead isotopic ratios in Avery Lake. Nonetheless, the XRF data suggests that biomass burning resulted in the deposition of around 0.4 tons of lead at Avery Lake during the bomber occupation. Significant amounts of lead were deposited in Avery Lake as a result of pre-Columbian Native American activities that involved both land use and long-distance trade or acquisition of Galena, followed by localized processing and utilization. During the Mississippian occupation between around 1150 and 1400 CE, lead isotopes indicate that Galena processing or use resulted in around 1.5 tons of anthropogenic lead pollution. An earlier lead pollution peak between 310 and 15 BCE during the bomber occupation, which lacked an accompanying lead isotope excursion, was likely the result of extensive local biomass burning. It is virtually certain that pre-Columbian lead pollution was not restricted to Kincaid Mounds. However, the spatial distribution of pre-Columbian lead pollution within the Black Bottom and indeed at other archaeological sites across the mid-continental United States is not known at this time. It is probable that other sites where Galena trade, processing, and utilization occurred also contain legacy pre-Columbian lead pollution, as suggested by increased lead in Horseshoe Lake near Cahokia during the Mississippian occupation. Detailing the spatial, temporal, and source variability in lead pollution provides important information about how pre-Columbian Native Americans interacted with and utilized their landscape and its resources.